Welcome to DP Tutorials by Donny Jarwa. In this teaching module, we will learn and emphasize on Wheatstone Bridge principle. This Wheatstone Bridge principle is a very important principle where it finds application for finding and determining the resistance of an unknown resistor. Now, it was first devised and invented by this scientist by the name of Samuel Hunter Christie, and he is the inventor of this principle. Yeah? He is the inventor of this principle. And way back, he invented this in the year of 1833. Yeah? But this principle, the creation of Christie was being popularized. Yeah, the creation of was being popularized by a British scientist by the name of Charles Wheatstone, and he was able to explain all the underlying principle of this idea in the year of 1843. So over here, when you look at this circuit arrangement, it consists of 4 resistors which are connected across the arms of a regular square. And from here, that means there is a principle which underlines this circuit arrangement. Now from here, the working principle of this Wheatstone bridge is that at balance condition, when we say balance condition, it means the galvanometer will not show any deflection, which means if the galvanometer shows 0 deflection, it means that there will be what? There will be no current passing through the galvanometer. That is point number 1. And in such condition, if there is no current flowing to the galvanometer, which means that current in the main circuit will be there, but at such cases, if no current is flowing to the galvanometer, then the bridge, then this bridge is said to be balanced. This bridge is said to be balanced if and only if, this is the condition, the product of the resistances of the resistors of the opposite arms are equal. What does it mean by that? See, if I take resistor P, opposite of resistor P will be resistor S. Now, if I consider resistor R, opposite arm or opposite resistor of R will be what? Will be Q. So which means if I multiply P and S, if I multiply P and S, it should be equal to the product of the resistance R and Q or Q and R, which is given by this. And after solving, we have to arrive at this condition. That means the ratio of these former arms, P by Q, should be equal to 1. P divided by Q should be equal to R divided by S. So here this will be R divided by S. This is our balance condition. This is what is known as your Wheatstone bridge principle, and this is possible only if the bridge is balanced under the condition that the current across the galvanometer should be equal to 0. So over here we have these resistors P, Q, R and S, which are connected across the 4 arms of the bridge ABCD. So over here I will name these points as A, B, C and D. Okay, these points A, B, C and D are junction points whereby we connect all these 4 resistors P, Q, R and S. And from here, since we have since we have this battery, let this battery be having an EMF. Okay, let the battery have an EMF E. Since the battery have EMF E, so we know that it will be having potential, and these are the polarities of the battery, positive and negative. Once we close the circuit, then current will flow in the circuit. So over here, okay, at balance condition, no current will flow to the galvanometer, producing 0 deflection. Another assumption, that I, okay, over here, let I be the current in the main circuit. So if I is the current in the main circuit, this current I is approaching point A. Okay, this current I, the current I, that current I, it is approaching point A. It is approaching point A. when current I is approaching that point A, from here this current I will divide, or it will be split into two parts. Okay, one part will be the current which move across arm EB, another current will be moving across arm ED, and over here there will be some current also which move across arm BD, okay, and so on and so forth. Then from here, let I1, okay, let me name this as I1, let I1 be the current across arm AB, and let, okay, and then I2 be the current across arm ED. Then from here, also let, okay, let IG be the current across 1. Let IG be the current across arm BD, okay, across arm BD. This IG be the current across arm BD. So from here also we have to apply certain rules in order to find the voltage drop across all these resistors P, R, and even this galvanometer G. So we have to apply Kirchhoff's voltage law. So here comes the underlying principle for applying those Kirchhoff's laws, okay, Kirchhoff's current law and as well as what? Kirchhoff's voltage law. So from here, let us consider in this branch A, B, D, A, and in not branch loop A, B, D, A, and in loop B, C, D, B. Okay, we will apply Kirchhoff's laws to find out the voltage drop across all those resistors. In this loop A, B, D, A, we will consider this is the first loop, and in this loop B, C, D, B, we will consider this as what? We will consider this as the second loop. Now on the first loop and on the second loop, we will take point A, okay, we will take point A as the junction point. Okay, we will take point A as the junction point. This point A will be taken as the junction, okay, as the junction point. The point A will be taken as the junction point, which means that the point will be stopped. Then from here, we have initialized that let I1 and I2 be the current across arm AB and arm ED respectively, and the current IG be the current across the galvanometer having resistance G. Now when you look at this diagram, when we apply these, okay, when we apply these Kirchhoff's current law and Kirchhoff's voltage law, you have to remember certain rules. Okay, you have to remember certain rules or convention in order to find the voltage drop. So from here, let us recall some of the rules and some of the conventions of Kirchhoff's current law and Kirchhoff's voltage law. So some of the rules from here is that if we consider on this loop E, B, D, A, if I take point A as the junction point, it is very evident that this current I1, okay, that current I1 is clockwise in nature. Okay, it is very evident that current I1, okay, and even this current IG, okay, both this current I1 and IG are clockwise in nature. Okay, are clockwise in nature, which means that this arrow representing what? This arrow mark representing the clockwise rotation or the clockwise movement of the current with respect to junction point A. So I1 and IG will be clockwise. So if both I1 and IG are clockwise, so it means that according to the sign convention, I1 will be positive, IG also will be positive, since they are clockwise rotation with respect to point A. Now, when we look with respect to point A on loop A, B, D, A, this current I2 is opposite with respect to this direction. So it is anti-clockwise. So which means that the current I2, this current I2 will be anti-clockwise with respect to point A. So this current I2 will be what? Will be negative. So which means over here that if we apply okay, Kirchhoff's current law, let us apply Kirchhoff's current law first at point B. Because why? Because we need to know what is the current along this branch, and we will also apply Kirchhoff's current law at point D so that we can establish what is the current across that branch DC. So in order to find those currents across branch BC and current across branch DC, we have to apply Kirchhoff's current law at point B and at point D respectively. So over here, when we apply, okay, let us apply Kirchhoff's current law first. Okay, first let us apply Kirchhoff's current law at point B. So when you look at point B, that means since this current I1 is approaching point B, okay, current I1 and current IG are what? These current I1 and current IG, they are approaching. Okay, they are approaching point B. So if these currents are what? Are approaching point B, so it will be taken as positive. So over here, the current I1 and the current I1 and IG. I1 with respect to point B, that means this is our point B. Okay, this is point B. I1 is approaching point B, whereas this IG is moving away from G. So you need to know how much is the current across this branch. So this current which is entering this point B will be taken as positive. This current which is moving away from point B will be taken as negative, according to Kirchhoff's current law. So you have to find what will be the remaining current across this branch BC. So the current across this branch BC will be what? Will be this one. The current across the arm BC, okay, the current across the arm BC will be equal to what? I1 minus IG. Okay, I1 minus IG. So over here, this current across this branch, okay, the current across this branch BC will be equal to what? Will be equal to I1 minus IG. This will be the current across that branch. Okay, this will be the current across that branch BC. Similarly, if you look with respect to point D, that means this is point D, then current I2 is approaching this point and current IG is also approaching point D. Okay, current IG is also approaching point D. Both these are approaching. So with respect to point D, that means I want to find how much is the current. Across this branch BD. That means this will be the current across this branch CD. So I2 approaching, taken as positive. IG approaching point D, also taken as positive. So this current across this branch, okay, this current across this branch CD will be equal to what? Will be equal to I2 positive, IG also positive. So this will be that current which flows across what? Across that branch DC. So at point B, okay, the current I1 minus IG, the current I1 minus IG will flow, okay, the current I1 minus IG will flow across what? Across arm BC. Okay, across arm BC. Now, if we again apply this Kirchhoff's current law at point D, if we apply Kirchhoff's current law at point D, we find that this current, okay, this current I2 plus IG, this current, okay, this current I2 plus IG, that current I2 plus IG, this current will flow, okay, this current will flow across, okay, that current will flow across, I'll just write in short, it will flow along the arm, along the arm DC or the arm CD, okay, DC. So those are the some of the applications of Kirchhoff's voltage law and Kirchhoff's current law. Now from here, we will apply Kirchhoff's voltage law on we will apply Kirchhoff's voltage law on this loop 1 and on this loop 2. Now when we apply Kirchhoff's voltage law on loop 1 and on loop 2, we should be very careful with respect to the sign conventions. Now from here, let us redraw. Okay, we have this is our loop 1. Okay, we have these are the networks. Okay, this is the loop A, B, D, and we have also another loop, okay, which is B, C, D. We have resistor P, over here we have voltmeter J, and over here we have we have resistor S. Current I is along this branch, current IG along that branch, and current I2 along that branch, step by step. Now when we apply Kirchhoff's voltage law on this loop ABDA, okay, when we apply, next we will apply Kirchhoff's voltage law at loop, okay, at loop ABDA. When we apply Kirchhoff's voltage law on this loop ABDA, we have, so from here, when we apply Kirchhoff's voltage law on this loop, that means we have to remember those conventions. Those conventions reminds us that the clockwise rotation of the current are taken as positive. The clockwise rotation of the current are taken as positive, which means that if I take junction A as the as our point A as our junction point, which means I1 will be positive, and this IG also will be negative. With respect to point A, this I2, okay, this I2 is moving in this I2 will be moving in the anti-clockwise rotation. So if I2 is moving in the anti-clockwise direction, so I2 will be I2 will be taken as negative. So if you multiply I1 and P, that will give us our voltage drop on branch AB. So over here, this will be I1 into P, okay, with the positive sign, plus IG into G, current into resistance, okay, current into resistance, and then with respect to I2 will be I2 will be negative, so that's why I write minus I2 into I2 into S. S is our resistance. Then when you look at this network, on this network there is no voltage source. If I consider on that network, there is no voltage source, which means there is no cell. If there is no cell, that means the EMF of this loop ABDA will be equal to will be equal to 0, which means that over here, applying Kirchhoff's voltage law on this loop will be will be I1P plus IGG minus I2S. This will be equal to this will be equal to 0. Let us mark this as equation number 1. Okay, when we look from equation 1, okay, when we look with respect to that equation 1, we find out that IP, okay, when we look at that equation 1, we find out that this IP, okay, this IP is clockwise, okay, this IP is clockwise. I1 will be clockwise in nature, that is why it is taken as 1, that is why the sign is positive. I2 is anti-clockwise, that is why the sign is negative. Even that IG will be clockwise in nature, that is why the sign is the sign is positive. When you look at that loop ABDA, why the EMF is 0? Why is it 0? Because there is no cell. If there is no cell, that means there is no voltage source, so that is why EMF will be equal to 0. Okay. Now, when we apply, let us apply Kirchhoff's voltage law. Okay, let us apply Kirchhoff's voltage law on the second loop. Okay, applying KVL at loop, okay, BCDB, okay, at loop BCDB. dB. On this loop BCDB, we have, so on this loop BCDB, we have resistor Q, resistor R, okay, resistor Q, resistor R, or resistor Q. Oh, wait, there's some mistake over here. Okay, in this this should be resistor R, so I will place over here R. Okay, so here let us write as R, and over here also let us write as R. Okay, and over here this will be resistor S, and in this point along this terminal D, okay, along that BD, we have the galvanometer G. Then we have these currents over here. Let us look on BC. On BC, the current will be what? I1. The current across BC will be what? I1 minus IG. But with respect to point B, now with respect to point B, this current I1 minus IG will be moving in the clockwise direction. And with respect to point B, IG will be anti-clockwise, and this current I2 plus IG also will be anti-clockwise, so it will be negative. So from here, which means that if we focus on this network BCDB, which is our second loop, this current across this branch will be what? Will be I1 minus IG. With respect to this point G, this current I1 minus IG, it is what? It is clockwise in nature. Okay, that current I1 minus IG with respect to this point B, it is what? It is clockwise in nature. So it will be taken as what? So it will be taken as positive. Now with respect to point B, look with respect to what? With respect to point B, look what is the sign convention for IG? The sign convention for IG will be what? Will be anti-clockwise in nature. Okay, it will be anti-clockwise in nature. So that current IG will be what? Will be negative in nature. Even this current across branch DC, okay, this current across this branch DC, it will be I2 plus IG. So this current I2 plus IG will be that current which moves across what? That will be that current which moves across the branch CD. Okay, will move across the branch CD. Even this current I2 plus IG, this current I2 plus IG also will be what? Will be in the anti-clockwise direction. So that current also, this also will be what? That current I2, okay, plus IG will be what? That current I2 plus IG also will be negative. So those are the some of the important sign conventions which we are used for what? For applying KVL on that loop. So over here on that loop BCDB, okay, on that loop BCDB, with respect to junction point B, current I1 minus IG, okay, I1 minus IG. This is the current across the branch 1, across the branch BC. So that current I1 minus IG will be taken as positive. Multiply this current with this resistance. Current into resistance is voltage drop. Then next, along this branch BD, but with respect to point B, this IG will be what? This IG will be anti-clockwise, so it will be taken as negative. IG, current IG. What is the resistance on this branch BD? The galvanometer G, so you have to write capital G. Then from here, another current across branch DC will be what? Will be I2 plus IG. Okay, this is the current across that branch BD or CD. But what will be using sign convention, what will be the nature of the sign of this current? It will be negative. Why? Because this current is moving in the anti-clockwise direction with respect to point B. So I will write here negative sign. But when you look on this loop BCDB, even over there also there will be what? No cell. So the EMF of such the loop, the EMF of such the loop will be what? Will be equal to 0. Okay, will be equal to 0. So from here, let us rewrite. This will be the current okay, across arm BC. Then we have this IG, capital G, minus, okay, I2 plus, okay, plus IG equal to 1, equal to 0. So let us mark this as 1, as equation 2. So those are the things that we have learned. So let us look from the main circuit diagram. Okay, this current, this current, okay, this current I1 minus IG with respect to point B is clockwise in nature. With respect to point B, this current IG will be what? That current IG will be anti-clockwise, since this is that direction. With respect to point B, this current I2 plus IG also it is what? Anti-clockwise in nature on the second loop. On the first loop, with respect to point A, I1 is clockwise. That is why it is taken as positive. With respect to point A on the first loop, on this first loop, IG is also positive. On the first loop, I2 with respect to point A, it is what? Negative. So these are the important things that we need to know. Then from here, we will apply some condition. When at balance condition, okay, at balance condition, the current to the galvanometer will be 1. At balance condition, the current to the galvanometer will be 1, will be equal to 0, which means that this current IG will be equal to 0. When IG is equal to 0, which means that there will be no deflection on the galvanometer. Therefore, these equation 1 and equation 2 reduces to the following step. Okay, over here we have I1P plus, in place of IG, we will put by 0. Okay, 0 into G minus I2 R, this will be equal to 1, this will be equal to 0, which means over here that this will be I1P, this will be equal to 0, so we have I2R, this also will be equal to 0, which means that we solve this particular relation, we get I1P. Okay, if we carry this to the right hand side, that means from negative it will change into 1, it will change to positive, so we get simply what? Simply I2R. So which means that over here, if we can write like this, okay, I1, the ratio of the current, I1 divided by I2, this will be equal to 1. This will be equal to R divided by P. Or we can use this relation also. Okay, we can mark that as, let us mark this as relation number 3, okay, the third relation. Also from equation 2, we have this condition, putting IG equal to 0, okay, on this IG equal to 0, all those terms will be substituted by 0. I1 into 0, then we have Q, minus, in this place of IG we will put by 0 into 1, into capital G, then minus I2 plus 1, in place of this G we will put by 1, 0, and over here this also will be equal to 0. Then when you solve, then this one will give you I1Q, this term will vanish, and then you will get only I1. Over here this will give you 1. This will, the resistor, we have forgotten to write the resistor, this will be resistance R, okay, this will be resistance S, I mean, so over here that is right, this will be S. Okay. So over here this will be 0, so minus I2 into 1, I2 minus I2 into S, this will be equal to 0. If we solve this, we'll get a relationship of I1Q. When we carry this term to the right hand side, that means that will be positive, so we get I2S. Then let us mark this as equation number 4. So when you look from equation 1 and equation 4, that means if we divide equation 1 by equation 4, or from here also we can rewrite in this form. Okay, I1 by I2, okay, I1 by I2, this will be equal to 1, S divided by Q. When you look from equation 3 and equation 4, if we divide, okay, if we dividing equation 3 by 4, okay, we have, or you can write like this, or we can write like this, 3 divides 4 implies, that means left hand side of 3 divided by left hand side of 4, right hand side of 3 divided by right hand side of 4. So we have I1P divided by I2Q equals sign IPR divided by I2S. So when you look at this particular relation, some of the terms will get neutralized. I1 will vanish, I2 and I2 will also vanish, which gets cancelled. So we get a final expression or a final condition of P by Q equal 1 equal R divided by S. This is our balance condition of Wheatstone-Bridge principle, and this condition is true only if the bridge is balanced. Okay? Only if the bridge is balanced. When the bridge is balanced, this condition will hold true. So in the exams, mind you that when, suppose if values of P, Q, okay, R is known, okay, when the values of P, Q, R is known, then you can find out the value of S, which is what? Which is your unknown resistance, okay, which is your unknown resistance. So keep in mind that this Wheatstone-Bridge principle, it is very, very applicable in the sense that we can determine the unknown resistance by only knowing the values of the resistance from the opposite arms, okay, without depending upon how much current which is passing through the bridge. Okay, so it is independent of the nature of current which passes through the bridge. So that is the most important peculiarity of this Wheatstone-Bridge principle. Just go through these lectures so that you will understand. Okay, thank you.